Oh, hello everybody. We're just now starting. We'll be waiting just for a few minutes to people to join us, and then we'll reconvene. Hi Tanya. We're just waiting for other students to join us as well. So we'll start about a minute, okay?
Yes.
All right. I think we'll have to start. I suppose it's because, we are running the lecture outside of the normal schedule. So even though some students last week indicated that they would join, probably that's not going to happen. So I'll just go through what I need to do, and you can also tell me if there is anything which you would want to cover, or if there's anything unclear. And I'll put the whole lecture on YouTube just so other people can watch it in their own schedule.
Okay. Yeah.
All right. So it's going to be a personal lecture just for you. But later on, I hope that some other people listen as well. Just give me a second. So I'm going to share my screen. Perfect. I hope you see my screen now. Can you just quickly confirm that you see it?
Yeah.
Perfect.
Lesson 5.
Thank you very much. I rely on you now, so unfortunately, that's what it is. In this lecture, I just really quickly want to cover the time series analysis, and then I'll just also talk a little bit about the final assignments, kind of react to a few emails I've gotten to, kind of see a little bit, to show a little bit clearer what is expected from you there. So time series analysis. Well, time series, as you can kind of figure out from the name, it's about models which which use time series. It's basically you basically take past data of any trends, and then you kind of trying to figure out first of all what's happening, and then in the ideal case you also use it for forecasting. So in this lecture, we'll talk about a few of them. We'll talk about the autoregressive models, we'll talk about random walks, and we'll also talk a little bit about moving average models. And I'll tell you what they are used for and what they are useful for. In your final assignment, on the other hand, we're using like a similar method, but like there won't be anything difficult. There is basically like there is an exercise on time series where you use dummy variables to kind of figure out like first the trend, but also the seasonality. And it's kind of like the same exercise as we did in homework, in the 5th homework, which now like majority of you have submitted. So first, autoregressive models. Basically what the word autoregressive means is that we model the future development of variable from the past values of the same variable. That's why is it autoregressive, because you use the same variable just to pay past data. So you basically use like a regression between the same variable to predict the future. So for example, if you take the stock price at the time t, you can consider it a dependent variable, and if you take the price of the same stock at the time t-1, so let's say yesterday, you can use it for estimating it for today. So that's what the time series, the autoregressive models are. Then we'll talk also about like seasonality, which there's a chart here which I just kind of like randomly picked, and it's for retail sales in the United States, in billions, how much people are buying every given month, and it's for many years. And surprise, surprise, people mostly buy stuff around December, just before Christmas. You can basically see that, like, the sales before Christmas always grow by like almost like like about 80% or every year. And well, that's a kind of like a huge swing. So like then like if you're trying to figure out how to actually model such a thing, well, first of all, there's a clearly a trend. It's a growing trend, which kind of slowed down after Great Recession in 2007, 2008, and then just like rebounded a little bit. So first of all, you have to like kind of like figure out this underlying trend, and then also we have to figure out this seasonality effect. How do you actually put it in your model? So the growing trend, you can either do it by some like simple trending methods, as we do in the exercise and homework, or you can use the autoregressive methods. And then for the seasonality, there's also a number of ways. The one which we use in our homework is the dummy variable. So you basically, in this case, because you can see that like every month has a little different pattern, but like that pattern kind of repeats. So like just after Christmas, in January and February, and almost nobody spends anything. Then in the summer, it kind of picks up, and then it goes on November, December. So like ideally in this case, what we would do is to like create a model which basically puts together, which basically gives a dummy variable to every month, and basically you would calculate the seasonal effect, the effect of every month, and you would add it to that underlying trend which we calculate separately. So underlying trend, and then a trend for every or influence of every given month. That's what you probably do. Yeah, so this slide basically just describes what I just said. And like, this seasonality, it basically exists in absolutely everything. Like, for example, in calculation of inflation numbers, it's a huge problem, because you can imagine it like, the sales after Christmas, or like the Black Friday, for example, it causes like a huge havoc in inflation. But you want to actually know what's happening in the economy, you kind of like ignore that like seasonal effect. So every time you calculate inflation, you kind of have to seasonally adjust it to kind of remove that effect from the data, because otherwise you would like basically see that that the prices are going up and down kind of madly, and nobody would actually know what's happening. Or like weekend numbers like quite often like cause a lot of problems. That's kind of like a typical now when we are all watching the COVID-19 numbers, you can always see that like, the numbers are going really high during the weekends, they go down, and everybody's just like, yeah, it's okay now. And then like, of course, on Monday, like new huge numbers of the infections or deaths come again. So like some better like websites like Financial Times, for example, they started removing the seasonal effect, the weekly effect, the weekend effect, while, for example, Czech Statistical Office or the Czech Ministry of Health still like kind of gives us their like unadjusted data, and people are just majorly confused about it. I'm just going to skip through it so we can get to the assignment. So I'm just going to go through it quite enough quickly.
Okay.
Yeah, in time series analysis, you might notice that there's a lot of trends which use natural algorithms to identify linear trends. That's again like kind of like related to like the financial analysis in stock markets and such. And that's because we measure stock market movements in percentages. So like if a stock grows 5% first day and then grows 5% the second day, it is an exponential growth. It's kind of like hard to see on such a small numbers like 5%, but like you can see that like the second day, if it grows 5%, it's actually more money than the first day because the base changes. And that's basically like the definition of the exponential growth. And kind of like if it goes like over time, you could see that like basically all you would see is exponential changes. And that's why if we kind of like tend to like use logarithms, we basically just take the axis, the y-axis, and like and make it logarithmic. So the what's happening with x in this case, for example, the stock price, is unchanged. Actually, I might have. I might have a slide over here. So basically, if the equation looks like this and there's an exponent on one side, if you just like make a logarithm out of the y, then like you can use like really nice linear trend on the other side. And like maybe again, kind of like a really relevant example of this happening is if you watch the infection numbers for COVID-19, you might have noticed that very often what they do when they showed you the charts of like how countries compare with each other, that they use the y-axis, the one which is like vertically on the left, that like it's always like logarithmic. So because otherwise like the trend would be kind of mad, with like the lines would like not be really comparable, because there's huge differences between 100,000 infections and like I don't know 1,000 infections. The chart would just look like really incomparable. But if you just like use a logarithm of it on the y-axis, suddenly everything looks much more reasonable. I don't know, like I'm not really sure if I'm getting to you now, so I might try to find that one is linear. This one will be logarithmic. So if you look at a chart like this, these are basically the charts of COVID-19 infections. You might notice that this this axis over here, the y-axis, it's logarithmical. Basically it goes from 5 to 10 to 20 to 50. Basically, like the differences between the numbers are much smaller, and that's exactly what it is for. Because basically, if the line here was straight, it basically means a simple simple exponential growth of, where the exponent, is equal to 2. But to kind of like show the but like you can see that the chart would be probably like, if they actually wanted to put this chart in a normal linear trend, you would have either two options. All the countries would be almost over here, and then like the few worst ones would be on the top, and wouldn't really have a like a telling quality. So what they do is they just basically like remove this, make this axis logarithmical. That's basically the same concept which is used in stocks as well. So you basically can just use a linear trends while you know that they are actually exponential. I hope it makes a little bit more sense now. You basically, people are used to linear trends and they are used to reading them. They always like a straight line, and they don't deal so well with exponential growth. So you basically make it easier for them by just putting that like exponential growth to this other side of the equation. So autoregressive models, very quickly, what is it about? As I said before, you basically calculate the previous, the future values based on the past values of the same variable, of the same factor. So for example, with inflation, what you do is you always take like the previous month's inflation, and you basically just calculate the future one depending on depending on like the underlying trend of it. So this is basically the quantification formalization of that model. So you basically always the xt at x at the time t is intercept, plus the the previous day's value plus some some kind of a slope added to it. You can use one value, one previous value, or it can be a more like previous values. Obviously, if you use more of them as you go back in the past, so like let's say this is the previous day, this is the day before the previous one, and you go on and on and on. This slope, which is the influence on each previous days on the future data, is kind of decreasing. So you might expect that like the B1, B2, BP, it goes down with the values, and always you have the error term, which basically just tells you how much off you are likely to be. There's a lot of problems with the autoregressive models, which I'm not going to really go into. There's a lot of restrictive like qualities of it. Mostly because you kind of expect for the model to work, you have to have a set mean, and if there's a drift in the data, you first have to take the drift out, then you have to calculate the regression, and you have to put it back in. But for the purpose of this class, I just want you to know that it exists and nothing really more. So let's go on. That's for the autoregressive models. A special case for autoregressive models is the random walk. I don't know if you ever heard about the random walk or not. It's a model which like originally was developed for Brownian movement. Again, I don't know if you know what Brownian movement is. It's basically if you look at the smallest particles in the matter, we basically use like some like really powerful microscope, and you look at what's happening in the matter. You see atoms kind of moving randomly around. They're basically oscillating, and random walk was a model which originally was created to describe what's the movement of the atoms in a matter. Surprise, this model is actually extremely surprisingly accurate also for stock markets, because if you look at the stock markets, what the stock prices are doing, they are kind of like moving almost seemingly randomly up and down. It's all coming from something called efficiency of the markets. Last semester we talked about the efficient market hypothesis, and which basically expects the markets to be efficient in a sense that like basically all of the information which is available in the markets is already always included in the price when you are about to make a trade. And what is left is a total randomness. And that's exactly what random walks are useful, because they basically just say, anything which can happen is totally random. But we actually know a few things which are useful, because if they are random, but they are random equally in all sides, we also know how much random they are. That means the likelihood of their daily move, and we also know the where the stock price should like most likely end up. So even though like it sounds like that we actually don't know absolutely anything, it's not really the case. We actually do know that the expected value in the future is always exactly the same value as the day before. And that might be kind of surprising, but maybe we can use a little metaphor for this. Basically, random walk, it got its name not from the Brownian movement, but from like another like a kind of like a mathematical I don't know metaphor, where if you are in a city, and let's say you are on a date and you just go for like with your date like for a walk, and you decide it's going to be a random walk, and you basically you just keep walking, and like at any junction you decide to take absolutely random decision where you're going to go. If you go left, straight, backwards, right, and you do it for a while. So what's the most likely place where you're going to end up at the end? The most likely place where you're going to end up at the end is the place where you started, because your walk is random. It just like works that way, like mathematically. And with stock prices, it actually works exactly the same way. So the expected value for a random walk is always 0. You basically make no move at the end. But also, what is the what is the expected error term? That means like what's your like average move every time you go? You just go to the junction, then you make a decision. Well, it's actually standard deviation of your, or like it's actually variance of your movements. So for a random walk, for estimating what's going to happen with the stock prices, you basically know the probability, the expected value, which is 0. You will not make no move, but you also know the likelihoods of ending 1 street over, 2 streets over, 3 streets over, 4 streets over for stock prices. You can calculate the likelihood of how far how many percent the stock moves. So, and it's very useful because for example, if you have a portfolio and you know that you can lose them more than 5%, then like you can calculate using random walk. You can calculate the likelihood of that happening. I hope it still somehow makes sense. I'm not going to go deeper in the random walks, so I'm just going to skip it. And so we can, and last thing which I'm going to mention is the moving average time series models, which, they kind of like, they are great for like, again, like removing seasonal effects from data series. So here on this chart, you see an example of the data series, which is extremely cyclical. There's always like 4 points in 5 points in a row, 4, 1, 2, 3, 4, and then starts over. And you can see it's always going up, down, up, up, down, up, down, up, down, up, down. So like, what do you do with this thing? Like, usually you need to kind of like in regression model, you can use the dummy variables, or you just can use like a moving average model where you basically just calculate that this like underlying trend of what's happening there. Formula how to calculate moving average. It's basically just a sum of a few previous days divided by the number of the days, or months or years, whatever the seasonal effect might be. you know, and like you can use it also in regressions where you basically take the previous errors and use it using that, like, you know, that error can be, for example, you know, quantified by the dummy variables, which we do in our exercise. So again, like, you know, to come to an example of like when it can be useful, the COVID-19 numbers, when they use, you know, when, you know, as I said before, like the better websites now, when they show you a chart of infections, what they usually do is they use a 7-day moving average to kind of remove the seasonal effect, which we would otherwise see. Let's see what actually, you know, for example, over here, yeah. You know, if you look at the chart, which I like pull out kind of randomly before, you know, it's a 7-day rolling average. So basically, any moment you see on this chart is basically an average of last 7 days, and that's exactly because, so like these numbers, they are not like jerky. They don't look like they're going up and down all the time, because you know, like because we get more tests over the week than during the weekends. During the weekends, like a lot of doctors' offices, a lot of labs are closed. You know, like even like healthcare medical as professionals needs breaks. So you know, there's just more tests being done, and that's why we see higher infection numbers, and that's why, you know, like the numbers will be all jerky around. And if you just use 7-day rolling average, we see a nice smooth lines, and it basically works that way for stocks as well, you know. So that's enough for the lecture. I would like to ask you if you still yeah, I see now that we have a few more attendees, which is great. With the assignment, do you want me to talk about something specific, or should I just jump into what I got emails about?
You can explain about it first, maybe.
All right. So like I'll start with what I already said last week, and that was, sorry, I'm just going to click to where I need to go. So for the assignment, you know, you have 2 documents over here, like 2 documents, 2 sections in Moodle. One of them is the assignment brief, and this is the place where you upload your assignment. You basically, you know, go here and you basically just like upload it in there. It worked before, so I hope there won't be any problems. Sorry, I'm just going to I probably should just I would like to change it to English so you guys just see what's happening in here. So the deadline is 10th of June, so still plenty of time to actually complete it. If you want to complete it sooner and you want your grade sooner, just let me know. I already see that somebody actually uploaded over here, so that's great to see that like it's like some people have already uploaded their work. With the assignment itself, I'm just going to quickly download it. This is how it looks like. You know, there are the requirements over here. You can, it's the best way it's to upload it either in PDF or in Microsoft Word, and you can also give me a supplementary Microsoft Excel file so I can check your calculations. Because if you have any mistakes in there, I would like to check it and tell you exactly what went wrong. So if you just give me results, I won't be able to do it. If you give me Excel, I will. And like, you know, then you basically always have the data plus, and like each of you have a specific set of data because this MN is derived from your name. It's the first, like, you know, there's a conversion table at the end of the assignment, you know, which you basically just calculate your MN. So, you know, if your name is Mohammed Gandhi, it's 13 because it's 13 for M and 7 for G from this conversion table. So your MN would be 20 because the MN is just like basically the 2 numbers together. So each of you have a specific set of data. and then like you basically just calculate. It's a small data sets, but they like all of the calculations in there kind of like repeat what we did in homework, so like, that shouldn't be really such a big surprise for you. So this is a normal linear, a simple linear regression. You just basically calculate like how this depends on that, and there's like a few calculation like applications system. So first questions. So first there is a calculate the regression, then substitute in the regression, and there is always there is also asking you about application of the confidence interval, which we didn't do in homework, but it's actually not so difficult. Like you basically, if you use data analysis tool, which which is in the tutorial, it gives you the confidence interval. So then you basically just have to substitute the upper and lower limit into equation, and it will give you the confidence interval, if it makes sense. So and it's only like worth a few marks, 5 marks. So you might just try it. Like each question kind of contains like so like there like, because otherwise you would just like repeat what's in the videos. So like each question contains a little bit of like something which is a little bit more difficult. So so I can see like who really understands it, and like who just like repeats what's done in the videos. So the second one, that's a fairly simple, again, regression. It's a regression which requires you to use one dummy variable. So again, you have price, which is Y, square feet is X, and this type of the property basically is a dummy variable. You have to assign a dummy variable. So either F or C you replace with 1 and 0, and then you just run the regression. This one, it's a little bit more complicated. You basically, maybe I can actually, give me a second. Yeah, I actually have here data from this exercise. It's a little bit different data, so I just don't show you the results. But like it's fairly similar. You can see that it's slightly different. So this is basically how you copy the data. Then you have to calculate your MN, and then you have to substitute. So I'm just going to do it really quickly. If you want to just replace in anything in Excel, you press Control H, and let's say my MN is 19, so I just like I have a space plus space MN, and I replace all with plus 19. So that will give me this. Now, of course, like it still doesn't calculate because there's the equation, the equal signs are not there, so I'm just going to add them very quickly. There's a faster way to do it, but I'm just going to bother with it now. Sorry, my mouse is getting stuck. So now you have the data, and first of all, exactly as I did now in a lecture, you first want to figure out what's happening in the data. So you usually just go like you highlight, because this is just a year and this is just a quarter. So I'm just going to like look at the trend of what's happening in there, and it's like a growing line, like maybe even like a linear regression would actually work in there. But there seems to be a little bit of a seasonality in there, like it basically goes up and down, up and down, up and down, up and down. So if I actually just run a linear regression in there, it would probably show kind of a systematic error in the residuals, which we shouldn't really do. So what you need to do is basically just assign a dummy variables to each quarter. So just to work the data set, what you do is first you need the number of data point. So like, if I go back to the chart, you see that there's an overlap, like there's an underlying trend, which needs to be kind of captured in the regression, right? So I can do it just basically numbering the points. So I'll just go data point, and then 1, this previous one, plus 1. I'll just number them. And then I want to assign dummies to these. So D1, sorry, D2. And you always, how many dummies there always is? There's always n-1. So if I have 4 quarters, I need to use 3 dummies. So 1, 0, 0. So that's the dummy for first quarter, 0, 1. 0 for the second quarter, 0, 0, 1 is for the third quarter, and the fourth quarter, because there's no dummy for it, it's going to be 0, 0, 0. And now I'm just going to copy it down. So, and now I basically have a regression set. It doesn't look like much, but it is. And now I just run the regression, which I can't do because I don't have because I installed my Office yesterday and I didn't install my analysis tool pack yet. So I have to do it now. So anybody who doesn't have it yet, you should definitely install it. Once more, I just go there, okay? File, options, add-ins. I choose Excel add-ins. I go on and I'll click this one in. Oh my God, it seems like it's already in there. Now I go data analysis tool pack. I choose regression. Y range would be my clients. X range should be all of my variables, which is the number of the data point in a time, and the dummy variables. Labels, because I highlighted the top. I hope I did. 1, 2, 3. Yes, I did. And output range, I choose it somewhere conveniently. I might also look at the residual plots just for fun. And here we go. And now to interpretation of the regression. First of all, my regression has a really nicely high R-square. So I actually explained a lot by it. If you look at the p-values, well, this one is not really significant, D2, but the other ones are significant at the very least at 5%. The data point definitely is that, maybe this one didn't have to be, there. Maybe like the second period probably doesn't have much of a seasonal effect. And yeah, so, and these are the effects of each of them. So basically that's what you need to do. And I just kind of did the calculation for you, so you know how roughly to do it. And of course, we would also like to check the residual plots to kind of see if they are random. They seem to be there. There is no, yeah, no, but this is pretty good. This is pretty good. You can, there's advanced tests which you can kind of compare the distribution of the residuals to normal distribution, because they should be normally distributed, but that's above the scope of this class. So yeah, so that's pretty much what you do in this exercise. Then of course it asks you to calculate the forecast for next few years, so you should do that too. And with the I'm actually asking you over here for 90 for the 90% confidence intervals. So I kind of didn't click it, so it shows 95. So just be careful if you run the regression once more. It's reset over here. I can choose a different confidence level. I can choose 90 over here. And that will give you exactly what I need to know, what you need to know. And with the, I got a lot of emails about the question 4. mostly because what we did in the homework was 2 asset case. This is 3 asset case. You have to be careful there. You know, it's slightly different calculation, and you know, I say over here use 10% as the smallest unit combination. So if I go to, sorry, just everybody still, sorry, I probably just share. I hope everybody sees my screen now again. I mistakenly closed it. Everybody's still in there? I didn't hear you for a while.
Yeah.
Cool.
Yeah, we are here.
So that was the 4th homework. I'm really sorry, my mouse is still getting stuck, so I'm have to use the computer mouse, and I'm not really used to it. So if I download the file, so this is the homework as you did before. You know, so just imagine that there is another column over here. Now my mouse stopped working completely. Here we go. You know, and I have no idea what kind of numbers we had in there. I'll just check quickly. Oh, I already closed the assignment. It doesn't matter. Then, you know, I can, I don't know, I'll just put like a random numbers in there, okay? And then of course you have correlations. This is between stock and bonds, so there's going to be 0.3 for, this is something 0.8. And now, you know, this table, you actually have to change it, right? Because again, you have another column over here. So what you start with is, you know, you basically put zeros over here, but then you like, you know, you start extending. So, you know, if now I need to have a few of them over here with it should be 9. Not really sure why I don't see the numbers over here. You know, now we basically have to extend them to the table, because sorry, once more. Forgot how I did it. So, you know, now you have 90 over here. This is 10, so this must be a 0. If this is 80, this must be 10. You know, and just to make sure that everything works, you should always sum all the percentages together, and they should be always 100%. So just to make sure that you're not making any mistake, 100%, and then you go on. And like always, you have to basically just check. So there was 10 of these, there should be 9 of these now. So now you just go 20%. And you go the same way as before, and All right, so I'm just like basically like listing here the like various mixes of the three assets. So, you know, in this portfolio, I have 100% stock, 0 bonds, 0 commodities. Then I have half stocks, half bonds, no commodities. And here I'm just basically just adding commodities. So the stocks and bonds, their share has decreased, and I go on and on and on like this, you know, and you know, eventually it should look something like this. This is again different data, so I'm not showing you a solution or anything, but it basically, you know, will end up looking like this. And there should be a 66 like combinations. Now, with the expected return, the calculation is fairly easy. You always basically just, you know, take the expected returns on each of the you know, investments, and you multiply them by you know, the share. So that's basically the same way as we calculate it in a homework. You just basically add the commodities. The unusual and unexpected thing, you know, with 3 asset portfolio is the variance. You know, you have to use a different formula. And if you go to the slides of the 4th lecture, very last slide shows them. So this is the formula for the variance which you should use. So just to like quickly explain what is it about, this is the weight, this is the standard deviation, so this is the variance of the asset 1, this is the weight and the asset 2, weight of the asset 3. And then, you know, it's kind of gets complicated because there's always 2 times first weight, second weight, intercorrelation between the first and second asset, standard deviation of first and second asset. Does it make sense? So if I go back over here, sorry, not here. Where did I put it? Over here. So expected return was fairly easy, right? So expected return is always the expected return of the investment times the share plus expected return times the share plus expected return of this investment of the commodities times its share. It's fairly easy. When I copy it down, what I have to do is to lock these parts. So it's the BCD. I have to lock the whole cell. By pressing F4, by the way. And now I can just calculate the expected returns for all of them and just really quickly check if it works. Weights are used, these are used as well. And now to the portfolio variance. As I showed you before in the lecture, it's this formula over here. So, and like, you know, I don't really want to do the whole thing, but like, you know, we can just start basically quickly. You know, so portfolio variance is, sorry, weight squared, so weight. And this is the little head sign or little roof sign, which I'm always struggling to find on my computer. 2 times the variance itself. If you use variance, it's already the, you know, this whole sign, the omega squared, it's variance. So you don't square it anymore. You don't square it twice. So that's what it is. Plus, and now basically just go time squared times this variance plus this weight squared times this variance. So it's the first part. Surprise, surprise, my variance is exactly as the variance of the stocks because there is no bonds and shares, but the calculation is still not done. plus 2, and now weight 1, weight 2, intercorrelation, and both of the standard deviations in this case. So, sorry, yeah, and it's always only between two assets. So let's say now I'm doing stock and bonds. So it's the time times weight 1 times weight 2 times intercorrelation between stock and bonds times standard deviation of stocks times standard deviation of the bonds. Still 180 because there's no, basically that this whole part is now 0 because there's 0 over here. And now I basically have to repeat this whole process twice. So again, 2 times, and now we'll do stocks and commodities. And now, did I do it correctly? You can get lost really fast. Intercorrelation, let's say this is between stock and commodities, times standard deviation times this one. And that's not correct. But did I do a mistake? There must be a mistake somewhere over here. You can get lost really fast, as I said. This is not correct. That's because it just didn't take. Weird. Simply didn't have to do it once more. Still 180. That's correct. Plus, and the very last one. So again, the weights. Sorry. Plus 2 times bonds times shares times intercorrelation between them times standard deviation of the first one times standard deviation of the second one, and the result better be still 180. And now when you want to copy it down, you have to put dollar signs everywhere where they need to be, which is not easy, but it's basically everything which is in the BCD column. So right, this one, B, here we go. And it's the variance. Here we go. And standard deviation, as you know, is the a square root of the portfolio variance. So all you do is you can use this square function, or you can use the basically you just like square it at 0.5, and I have to put the correct kind of comma in there, and that's your variance. Does it make a little more sense now? I kind of show you the whole thing, so I hope that there won't be any more like unclarity about it. So yeah, so this is basically how you do the question 4 in the assignment. All right.
Yep.
Yeah. Thanks for
So that's pretty much it from me today. So if you have any questions, now is the time to ask. And if not, so thank you very much for coming up today. And I apologize for like holding the lesson out of the normal hours. Again, I try to compensate by like sharing the lecture with you later on. But yeah, this time has been difficult for many of us. So thank you very much once more for coming up, and I'll be looking forward to your final assignments.
Thank you. Have a nice day.
Yeah, you too. Bye-bye.
Bye-bye.
Bye-bye.